Good morning, everybody. Thank you for coming in so early. Welcome to the motion planning lecture. And as we are at the beginning, maybe I start just with a little introduction. My name is Wolfgang Hönig. I'm an assistant professor here since basically April of last year. My lab is the Intelligent Multi-Robot Coordination Lab, and I lead the multi-robot systems kind of subject area here at TU Berlin. And so my research mostly focuses on multi-robot systems and flying robots, but also in that context, we are often interested in motion planning. And just to give you a bit of background of my experience, so I have a diploma in computer science from TU Dresden, not far from here. Then I went to the United States and did a master in robotics and also a PhD in computer science with emphasis on robotics. Sure, please do. Yeah. And I think some other people also grabbed chairs from neighboring rooms. If you want to try, you can do it. Just return it afterwards. Then I stayed in the United States for a little bit and did a postdoc more in aerospace, which makes sense since I work on flying robots. And then I was a group leader here at TU Berlin, and then for 2 years. And now I'm an assistant professor. And I also did a few kind of industrial things, but fairly short. So I did internships at NVIDIA and Amazon Robotics. And I also worked at a small flying robot startup called Bitcraze in Sweden for a few months. And so what does motion planning look like in my research? Here's one example from a paper that's now about maybe 5, 6 years old. So as you can see, we have flying robots that are in a known space, and there's a lot of clutter in that space, and we were kind of interested in planning the motion so that the robots avoid a collision. And that's quite tricky for these flying robots because once they fly on top of each other, there's an effect known as the downwash effect, which basically causes some aerodynamic interactions which need to be avoided in order to avoid crashes. This lecture, like the whole class basically, is co-taught with Dr. Andreas Otte. So Dr. Otte is right now a staff scientist at Real-Time Robotics, which is one of these exciting robotics companies that have an office in Berlin. He also has some experience with TU Berlin because he did his bachelor and master's here a few years ago. He did his PhD in France, I think in Japan, a postdoc. And now he is a staff robotics scientist. And the way it will work is that roughly half of the lectures will be held by me. Half of the lectures will be held by Dr. Otte. So in particular, next week, you will meet him. And we also prepare jointly, so you get kind of a perspective of not only the academics, but also the real practical things, since he works in a company that is in particular interested in making motion planning fast and usable for real robots. Maybe also to show a video of some of his research, which is maybe now quite old, but still interesting because it's this very high-dimensional humanoid robot which has to move in this kind of rough terrain. And for that, you really have to plan where you want to put the foot. And once you decided where to put the foot, you also have to figure out what to do with all the joints in order to not tip over. And you can see here users can change things interactively, and then the motion plan also reacts to it, which means you have to be fairly fast. You can't spend hours on finding a solution. This class will also be supported by teaching assistants. We will have 3 assistants this semester. All of them are PhD students in my group. They will lead the discussion sessions that we have later on, and they do have background also in the area, so they do research on motion planning, on controls and robotics, and also, of course, multi-robot teams. And you will meet a subset of them tomorrow in the discussion session, the first one. Okay, so now we did some introductions, and we can maybe talk a little bit about kind of the class structure and the organizational things before we also jump today into some topics for motion planning. Okay, so let's look at that. So what is the class format? So it is a portfolio format, and we will have these lectures like today. They're 90 minutes long. They're prepared basically by either Andreas or me or jointly, and then presented by one of us. Maybe at this point I also want to apologize for the time. So the way it works is that this particular year we tried to avoid overlap between different robotics classes, so that people can take 2 or 3 robotics classes in parallel. But that created a lot of constraints in terms of room availability and instructor availability, and that is like basically centrally solved by a nice optimization problem. But in this case, the output was maybe not so good for the motion planning lecture. So I do appreciate that all of you came that early. We will make an effort to record these lectures. That's why I have this like microphone here. We did that also last year, but there were occasionally problems, technical difficulties like running out of battery or whatever, running out of storage. So it's kind of like this best effort thing. If it works, we will upload it. If it doesn't work, we will not upload it. And the idea is not that you kind of sleep long, but more that if you can't come because you work or you're sick or you have some other commitment, you have the option to really follow the lectures. I also do believe that it's kind of useful for exam preparation, because then if there's one particular topic where you maybe don't remember exactly what we said for a particular slide, you can go in the video and just listen again if we had some more insights while we explained it. So that much about the lectures. Then we have weekly exercises. So these will be maybe also unfortunately, but already tomorrow. So this is like kind of very short time span. Maybe we should more call it a discussion session. So what will happen is that we post an exercise sheet, which you already can find on ESIS right now. And then in the discussion session, you can discuss it. It will be kind of a theoretical part, which is very similar to what you will find maybe in the exam at the end. And occasionally there's also a kind of programming part. And I talk a little bit about kind of the discussion sessions in more detail how it will work. But the key idea here is that it's supposed to be interactive. I try to do the lecture also a little bit interactive, but it's a kind of a lecture. But for the discussion sessions, we also often do it flipped, so that you try to maybe explain to each other how to solve a particular problem, just to get more engaged. Since it's a portfolio format, there's all these like little things that you can do to gain points. And so in this semester, we will have 4 programming assignments. The assignments are individual work. So of course you can kind of talk high level to each other about it, but you shouldn't really discuss kind of concrete lines of code or whatever. And they do make up quite a lot of your grade, so they are important to us. And it also means that you get more of a hands-on experience on solving these sort of motion planning problems that we're interested in. historically, we don't really have fixed office hours. We do monitor ESUS very well, so you can ask there. You are also more than welcome to kind of request a meeting time, ideally with a proposal of when you are available, and then either the teaching assistants or myself will like propose the location and we can meet and discuss things. Most of the time in the past semesters, that has only happened kind of right before the exam, naturally, but you're more than welcome to do it in the semester as well. Yeah, maybe that's what I want to say here. Then grading. So I already said it's this portfolio style format. Maybe the exercises are the most unusual what we will do. So this semester we will try to do a voting system that you might have seen from Professor Toussaint's classes, like optimization algorithms or robot learning. So the idea is that you try to attempt solving the exercises beforehand, not all of them, just maybe pick a task that you like, try to solve it, and then before the discussion session, there's like a little form where you can just check, oh, I did this, I did that, and then we will randomly in the discussion session select one of the people who have selected that they are capable of presenting it, basically. And that should hopefully foster interactions a little bit. And then we do understand that some weeks you will not be able to do it. And then of course you can also instead submit your solution. Now the submission time is of course not before the discussion session. That doesn't work with a one-day span, but you will have typically a week. So yesterday we posted the first exercise, and then I think the deadline is kind of the Wednesday after. So next Wednesday, midnight or so, you can check on ESUS, is the deadline. Which also means that, let's say you said, oh, I worked on something, you go to the discussion session, you're not selected to participate because it's a portfolio format, you still have to submit to gather points. If you're selected, then you're done. And then ideally, when you do submit, it should be more than half of the exercise, and it should be written up by yourself. Of course, it will be after the discussion session, which means you most likely have seen the solution already. So it's really more about than making sure you can write it down yourself. So it shouldn't be too hard. Yeah, in total you can get kind of 10% or 10 points, however you want to see it, for all of these exercises. This semester there's, I think, 1 week is kind of holiday, so we have in total 13 weeks, which means, for 3 exercises you can just not do anything and still get all the points. Yes, maybe that's all about the exercises. And tomorrow the TAs can also explain it again if it's like unclear, or you will see it the first time live. Programming assignments, that's also exciting. So we will have these 4 programming assignments. Each of them carry a weight of these 10% or 10 points. It's individual work. It will be roughly every 3 weeks. We use GitLab for like giving you the assignments and also for kind of the final submission. The topics are also here. So the first one is kind of helper functions for motion planning. Then there will be one where you implement your own motion planning algorithm. One where you use a very popular library that's to solve more challenging problems. And then one where we really look at how to apply optimization to motion planning. Maybe I say something compared to last year as well. So we started this portfolio format last year as well. In particular, the programming assignments were, let's say, a bit more chaotic because there was no immediate feedback So students would submit, then the TAs tried to run it, and then there were maybe the scripts were named differently or whatever. And it was very difficult to even run the submissions. Which means this semester we will have a more immediate feedback. So whenever you push, there will be some tests run, and you should get a few minutes later, hopefully, some sanity checks at least. For grading, we will run it on a more difficult set, but you will at least have some of these like more simple example instances given before you submit. Which also means that hopefully it will be less stressful for you to work on it. You can have fairly high confidence if you pass the test that you will get a pretty significant portion of the points, and it will also be less stressful for us because we don't have to deal with small technical issues and can focus maybe on the algorithmic challenges that you faced when you implemented these things. And then finally, there will be also a written exam, which is quite heavy in terms of percentage, so it's 50%. It's 1 hour long, and it will cover all the topics from the whole semester, so there's kind of no midterm that you sometimes have in these portfolio style classes. And in terms of style, it will mostly cover the exercises, a little bit of the programming assignment, but obviously not to the point where you have to memorize anything. I think it will be open books. That's kind of what we did last time, but don't be too happy about it because 1 hour is challenging. So if you go and then you look things up, you solve the first task and you're not done, right? But we don't want you to kind of memorize definitions or these sort of things. Yes?
Online or in person?
In person, which unfortunately means open book, typically means no electronics unless we can somehow be certain that there's no communication, right? So in the past, I think we did allow like Kindles or these sort of things where it's fairly difficult to chat during the exam, but yeah. And we will also provide at least one of like the example exams from maybe last year or something, potentially without the solution, but you will at least see the questions that we have to discuss still. Okay, any other format questions? Yes?
For the exercises for the 1%, do I need 100% of the task from the exercise, or when do I get the 1%?
No, I think about like 75% or so, at least attempted, and then maybe more than 50% actually correct.
Will you say on the exercise sheet how many we need to have for the 1%, or will you say in advance, or how do we know how much we have to do?
So the exercise sheet will always have a varying number of kind of tasks, right? Like usually maybe 4 that are roughly kind of equal weight. And I would say you should at least attempt 3 out of the 4. And then ideally have like 2 out of the 4 also correct.
Okay, thank you.
Yeah. Any other questions grading wise? Okay, well, we will have more time later also. Then let's maybe talk briefly about the prerequisites. So most of the programming assignments will be in Python, so ideally that's what you know. We try to be somewhat language agnostic, so in theory you could write it in another language because most of the programming assignments are such that there's some input text file you read and you generate some output text file, and we just run something in between, but we didn't have that case yet. And then one of the libraries is internally written in C++, like OMPL, but it has Python bindings. So it can be sometimes helpful to at least be able to read C++ to understand how it works internally, but you wouldn't need to write it. And then, of course, in terms of the lecture, we will kind of use pseudocode, most of the time also inspired by the syntax of Python without calling exact functions that exist, right? So here's one example on thought how the A star algorithm that you might have seen before looks like. And I hope you have seen that before. The only difference is maybe that we use this mathematical notation in between, for example, the empty set function. Yeah, and then, excuse me, in terms of mathematics, we also require some basic mathematics. You will see some examples on how bad it gets today, I think, when we talk about definitions. But it would be good if you kind of can read sets. So that's kind of the union, and that's the intersection of a set. And usually sets we use is like curly letters, so these calligraphic letters that you can see here. Probability theory would be useful when we later talk about some of the proofs. So the second line is just this Bayes theorem that you hopefully have seen before. And then also, especially for optimization, linear algebra and calculus will be quite useful to at least follow some of the things. And then, if you're not sure, there's also some kind of write-up or tutorial that Professor Toussaint has, and you can't see it on the slide, but it's actually a link. So when you download the slides, you can click on it, and it should take you to that tutorial, and you can check it out. Okay, and then what are we going to do during these 13 weeks? So basically the class is structured into these kind of 5 areas of interest. So we will first spend about 2 weeks, including today, on foundations, which means what is motion planning, how can we formally define it, how do some of the concepts work, like collision checking, and other important terminology in our domain. And then we kind of branch out sequentially, but we look at 3 different classes of algorithms that can solve these sort of problems that we defined at the beginning. And so the first thing we look at is search-based methods, which is basically A star and variance, but we do get a bit more advanced than what you might have seen from like an undergraduate, let's say, data structure or algorithms class. This specifics for motion planning. The second and potentially biggest and most important group is sampling-based planning. Most important, I say, because that is still the method that most people would try first when they attempt to solve challenging problems, and where also a lot of research still lies. And so we will spend 5 weeks on it. So we look at important algorithms. If you have taken the robotics class by Professor Brock, you've definitely heard of RRT before. But we will dive into many variants of it and also look at kind of some of the proofs on how can we actually show that those are good algorithms. So that's what sampling theory, and OMPL is this open motion planning library, where we will also have a lecture that just kind of discusses the structure and the history of that, which is very important for kind of practical things. And then we spend 2 weeks on optimization-based methods. So if we have problems that are differentiable, mostly, or also some methods that work on non-differentiable problems, and also look at different algorithms in that context. And then we finalize with kind of 2 weeks of current and more advanced topics. So one important thing is that we actually try to then go back to all of these methods and compare them. What are the pros and cons? In which case would I use what? We look at hybrid and multi-robot approaches, and also a little bit on machine learning. Although this year we will reduce it because there will be more of that in the robot learning class that happens in parallel. Yes, and then there's 2 public holidays that kind of affect this class. One is Wednesday in 2 weeks, and one is Thursday in 3 weeks. And there's kind of no special plan, so we will just skip the lecture, and then we will have to see which of the exercises are even doable. That might mean that on, what would it be, May 2nd, maybe the exercise or discussion will be very short. So we will see how it goes. Okay, so that's roughly the plan. And then maybe it's also good to try to relate it to other classes in case you're right now unsure, or what should I actually take, or how does it relate to something that I already have taken. So at TU Berlin, Professor Toussaint has these optimization algorithms, and I also just mentioned optimization. And so in the optimization algorithms class, the focus is really on how optimization problems are solved internally. So the algorithms to solve some problems that you write down. Here in our class, we are more focused on how to write it down. So given some sort of problem, or we want to have a humanoid robot moving from A to B, how can I really formulate it so that an optimizer, an out-of-the-box optimizer, can solve it efficiently. But we don't look at how the optimizer works internally at all. Then we have robot learning, which happens on Tuesday this semester as a new class. And there we focus on how to apply learning to these typical robotics problems. And that, of course, also includes motion planning. So in some sense, this class will be useful to understand more in detail how motion planning, classic motion planning works. And then in the robot learning class, we look at how can we improve or accelerate some parts using machine learning to maybe find solutions faster. And then finally, we have this robotics class by Professor Brock, which is kind of more an hands-on introduction to robotics, which really spans all the different areas that we have, including some motion planning. And so if you have taken that, you have seen and maybe also implemented part of RRT already. Yes, and then there's some kind of other classes here. And again, those are, if you click on webs, it will be just a link. So you can find these classes if you just want to check it out. Most of them are fairly different from what we do here. Just because they also don't have these 3 foundational areas of planning algorithms. So most of the classes just pick maybe one and then teach a whole class on one of them, but not this unified approach. Okay, and then where can you find maybe more materials? So the classic textbook is this first textbook by Laval, Planning Algorithms. It used to be a great book, but it came out in 2006, which is now a long time ago. And so a lot of these things that are kind of currently common knowledge, I would say, are actually not in the book because they happened after 2006. But some of the basic things and the definitions are really nice in that book. And it also has a bunch of algorithms that we will not discuss because I would call them obsolete now, but that might be interesting from a historical point of view. And then the other 3 books on the right-hand side, they have at least some chapters on motion planning, and some bits are quite interesting. And there will be at the end of the lecture usually also suggested reading, where I point to maybe more concrete sections if you're interested in it. You don't have to look at it, shouldn't be required to get an A or anything, but sometimes you want to dive in a bit deeper. Okay, and then what is our goal for you at the end? So we want you to know what are the state-of-the-art methods to solve motion planning problems, to kind of figure out, to decide, given some problem, which algorithm should you use, or at least try to use, because sometimes it's a little bit trial and error. Also, we want you to understand the internals of the algorithms, which means you should be able to implement some of these things. and ideally also some of the theory. So what are actually the properties of these algorithms, which help you decide as well. And then since it is this portfolio format where the programming assignment is quite important, we would also like you to be able to use these kind of typical software packages that people in both academic and industrial areas use for yourself. Okay, so now I talked for about 30 minutes just to give you an introduction. Do you have any questions regarding the class format or, yeah?
This is my first master's semester, so I have an robotics one. From what I understand, it is still okay to take this class, not a prerequisite, or what?
Yeah, it should be fine, I would say.
Okay.
Yeah. Any other questions? Okay, then let's continue, or actually start with real topics today already. All right, so introduction. So what we can see now is that robotics becomes more and more important in different areas and also almost hidden. So if you, for example, order something from Amazon, there's these warehouses that are actually run to a large extent by robots. And what the robots do there is that they go pick up these shelves in blue and bring them to some area where typically right now a human stands and packs the boxes. But of course Amazon is dreaming about replacing the humans as well. Just picking is quite challenging. But this sort of automation in industrial settings is actually very common. We do have self-driving cars to some extent, not so much on the roads maybe in Germany, but if you go to San Francisco, you can even order a Waymo cab and sit in it and it's actually driving. And yeah, you should hope that kind of works. And then also home robotics is quite important. So these vacuum robots are very common these days. And so, of course, for us the big question is, what do we need in terms of maybe engineering skills in order to make such systems work and also to improve the existing systems of today. And so the maybe classic robotics pipeline that some of you might have seen before is that we can kind of split this task of doing something in an automated fashion into different building blocks. And so the first building block would be some sort of sensing. So we have a camera or a LiDAR or any other sort of sensor. We take that input and then we try to abstract away some interesting information in our state estimation. Like for example, where's a pedestrian or where am I in my own world? Then I make some sort of decision based on what I have observed and what my prediction is, what is going to happen. I decide what I will do next on a more or less high level. And then I have a controller that tries to execute this decision to the best possible ability. And then typically I actuate, there's the environment, there's some sort of physics happening that will change our state, and then we kind of repeat it in a loop and we sense again and so on. Okay, and then basically we are here in motion planning, which means we are just part of this decision, this tiny module as it's called decision making. And intuitively our goal is, or the problem specification that we have is that our robot should reach a goal given like some sort of representation of the environment, given our current state and the goal state without anything bad happen. And classically bad happening meaning we collide with either static obstacles or other robots. And maybe just like some sort of caution here. You will also see that more in the like robot learning class, but in modern systems we don't necessarily have this sort of separation in these four groups. Some of them might be fused together and you solve them jointly. And of course that's the same with motion planning. I mean, if sometimes you combine motion planning and control, for example, and then that would be fused. But in terms of just studying it, I think it makes sense to look at these four-stage pipeline and focus for a moment just on the aspect of decision making. Okay, and then where is it relevant? Well, the most obvious case is mobile robots. So any robots that can move around, like as a rover on Mars is quite important because you have kind of this very long delay for communication, so teleoperation is a bit difficult. So it would be nice if you could just high level say, okay, in the next 8 minutes, move there, and I will just execute it. Self-driving cars, vacuum robots, warehouse automation we already had. And then also flying robots, since that is my specialty. There's a problem is, for example, there's now these commercial drones that just work as an external action camera, I would say. So you can walk around or do some sort of sports and it will automatically track you, and at the same time it has to avoid collisions with trees in the forest, for example. Maybe also quite obvious is that for manipulation robots that are not directly mobile, they're typically fixed somewhere on a table or somewhere else, you do need motion planning because you need to decide what the different joints are doing. And those manipulators are used quite a lot, of course, in manufacturing, but also in robotic surgery, for example, which becomes more and more common because it's faster and to some extent also safer. And more of these fun things like cooking robots, which also already exists in some of these, more like a gimmick or so, but maybe I think it was in San Francisco they had, for example, at the airport this robot that can make you a coffee like a barista, and it was largely based on a robotic arm. Maybe what's not as obvious is that it's also quite important in things like computer games. So a lot of kind of the fundamental work in my area of multi-robot systems has started out actually in like the gaming industry, because there you have this problem of many different agents that need to do something and shouldn't collide. And also for kind of these disaster modeling and avoidance, there's this crowd simulation is very, very important to figure out what would happen in case of some bad event. Is there actually enough kind of escape routes and so on. And also motion planning, very important. And then it turns out that it's also useful for things that don't even look like computer science or automation that much. So, for example, in biology, a lot of these problems can be framed as a motion planning problem because motion planning is just some sort of decision making in high dimensional spaces. So for drug design or protein folding, you can apply some of these algorithms, especially the sampling-based algorithms, to try to find solutions. And then, of course, not all modern robots can be put into these categories. You see more and more hybrid systems. There's this like spot robot where you can put a manipulator arm on top, so it's like a manipulator plus a mobile robot. There's these humanoid robots which kind of encapsulate a lot of different things. And I think it's important to keep in mind, even though we might study here in the class fairly simplistic problems to make a point, that the application is very widespread and that we try to make a decision where both the spatial domain and the temporal domain is important, right? Like we try to avoid spatially these collisions, but also we try to reason over some fairly long time horizon in some cases. And that also means that some of these solution methods we look at will transfer to other decision-making problems in principle. Okay, so how did motion planning start? So that's maybe also interesting. So actually this algorithm A star is not that old. So it was developed at this research institute in 1968. And then it kind of worked. It was a proof of concept, had a nice proof also back then. But then really people looking at how difficult motion planning itself is took another decade or so. And yes, we look at that a little bit later, but the result is quite negative. The p-spaces means it's quite complicated. And we discussed that later in one of the theoretical classes. Not surprisingly, if you have multiple robots, it doesn't get easier. Luckily, also not harder. So that took another while. And then collision checking came out in '88. I believe also more in like the gaming sequence. And then the sampling-based planning, which we discuss quite in some length, was just kind of originally invented in '96. So kind of about a decade before this book was written. And of course, since then, a lot of things have happened. So around 2010, there was this, I would say, rediscovery that one can use optimization. Rediscovery because in kind of the aerospace domain, people had, of course, used it long before for problems that we would now call motion planning problems to like get rockets to fly, for example. The motion planning library was also roughly developed around 2010, so it's now a little bit more than a decade old, but very well maintained. And so in the last decade, since the book came out, a lot of things happened in terms of more hybrid approaches, combinations with machine learning, and so on. Okay, and just to maybe give you an example, you can test motion planning problems also in the browser. When I checked this morning, of course, the web page was down. Otherwise, I would show it online, but it does run. Do I have it here? I have to just move it over. Okay. So basically, there's some Docker container you can also run locally, and then it's like the web page running. And the way it works, so now I have these two screens, it's a bit annoying, but you can define a problem, and then you can select the planner here, and then once you're happy, you can solve, and then hopefully it's always more fun to see an animation. So this is what we know maybe as a kind of geometric motion planning problem or pianos movers problem. So we have this puzzle-like piece that has to go through some sort of difficult obstacle-rich space and get to a goal. And you saw it was fairly quick, just running on my laptop, basically finding a solution so it doesn't look too bad within like, I don't know, 2-3 seconds or so. And yeah, here you can kind of play a little bit with other sort of little problems, look at it in 3D and so on. So feel free to try it if the web page comes up again. Otherwise, you will be able to play with it a little bit later when we discuss OMPL as well. But just to kind of give you an impression, it is quite mature already. There's these tools where you can just define problems and you can solve it. Okay. Okay, so let's now look at it a little bit more formally after we have maybe informally defined how motion planning looks like. So let's take, for example, this Ducky Town example, where you have all of these kind of cluttered obstacles and you have a robot that should move around. And so there's kind of two ways to, like motion planning, you can see it in two ways. Like the first way would be, okay, I pick up this robot or one of the ducks and put it in my hand and then I move it around. And then obviously if I do that, I have quite a lot of freedom because like with my hand I can move it everywhere. The other option would be maybe I have some sort of remote control and I can directly control the robot. Then I'm much more constrained because I can suddenly not move in the third dimension anymore. I'm constrained to kind of the flat space. And typically I can also not immediately like start or stop. There's some sort of acceleration and deceleration. So there's these different ways of moving it. And then of course the question is also what is a best solution? And that depends on the task at hand. So if it's a racing course, then maybe you want to go as fast as possible. But you could also imagine that you might want to minimize the energy that you need to go to a goal, or maximize the observations that you get on your way. So if you do a holiday trip, you want to maybe see the most sights and not just be quickest again at the airport. Okay, so how can we abstract that away? So for now, let's say we focus on 2 dimensions, and then we could say, okay, we just look at a finite dimensional space, so a fixed workspace like the room here, that is kind of this sort of rectangles that we have with some coordinate system. And then we could say, okay, all of the entities we are interested in are just simple 2-dimensional shapes. Like for example, the obstacles marked in gray here are just sort of rectangles. The robot, the car in blue, is also a rectangle, and then the goal state is just drawn in this outline over here. And so before we can actually define the problem, we have to look at some of these formal notations. So the first important one is what's known as a configuration. So the configuration is some sort of vector that just specifies either directly or indirectly exactly where every point of the robot is in space. We see some examples later on. Then degrees of freedom is actually just the minimum number or the minimum kind of dimension that you need to encode the configuration. And then the configuration space is just containing all the configurations that the robot might have. And so typically we also use, instead of configuration space, we also sometimes say state space, and we sometimes say state instead of configuration. Maybe like the notation helps before we start with an example. The configuration space, or the configuration we call Q, or if it's a state X. Then the degrees of freedom, we don't really have a notation. And then configuration space itself is this calligraphic Q, and then any configuration is just an element of that set. So it's just a set that contains all the configurations. If we use the state space, then we often use this calligraphic X instead. Okay, so that's kind of very abstract and annoying definition. So let's look maybe at one example. So on the right-hand side, I have written again just the definition. And then on the left-hand side, there's our example. So we have a robot that is really just a single point in space. And the robot can move just in the 2-dimensional x, y plane. So what do you think is the configuration, the degrees of freedom, the configuration space in this case? Let's skip the workspace for now. Yes?
So maybe the configuration would be XY.
Mm-hmm.
Degrees of freedom are 2 because we have 2 variables in the configuration.
Yeah. And any opinion about configuration space?
That would be the plane, the XY plane.
Good. Exactly. And so in this case, R2 could be maybe more specific if we would say it's somehow bounded, right? But in the picture, we don't see that it's bounded. And then workspace, I didn't introduce the definition, but it basically is either the 2-dimensional space or the 3-dimensional space. Never higher dimensional, so it's just kind of the physical spatial world that we are in. Okay, let's do another fun example. So here we have a door. The door is fixed, but it can be opened and closed at this angle theta. So same exercise. What would be the configuration, the degrees of freedom, configuration space, and workspace? Yes?
So the configuration would be the angle theta.
Mm-hmm.
And the door is 1 degree of freedom. And then the C space would be like depending how far the door opens, so 0 to pi, I guess.
Mm-hmm.
Or, I mean, maybe not pi, but somewhat close.
Yeah. And workspace?
That would be R2 as well.
Could be.
Could be.
I mean, it really depends. Like I wrote R3 because it's like this 3-dimensional picture, but if you would look at it from like this top-down view, it could also be R2. And then maybe what's important here is that for the configuration, it doesn't need to be minimal. So in principle, we could also have as configuration all the points that the door kind of occupy, like the volume that it occupies, and then the configuration would suddenly be 3-dimensional, right? But that doesn't change the degrees of freedom, because the degrees of freedom by definition was a minimum encoding. And typically that goes along that one picks the also minimum encoding for the configuration, because that saves memory, right? Just in terms of definition, we have the option here. Okay, and then I have another example. So now this is a bit more complicated, so I maybe have to explain it first. So we have this car-like vehicle over here. It has a front steering, so the wheels can turn a bit, given like this angle, which gives us the turning angle. The car has some length L, that just is the distance between the back wheels and the front wheels. It has some sort of center that we randomly defined to be kind of on the back axis of the car, and that just defines where the position is. And then we also have, again, another angle theta, and the angle theta just tells us which orientation the car has in the space. Yeah, and it's kind of like top view, similar to the picture down here, right? So the blue thing would be the car, and the car can, of course, turn also. And the question is the same: what is the configuration, the degrees of freedom, the configuration space, and the workspace in that case? Okay, yes?
I would say the configuration might be X, Y, and theta.
Mm-hmm.
So basically the position and the orientation.
Yep.
Yeah, the degrees
freedom, I don't know why, but I kind of think it's just 2 because can move like, I don't know how to like put it, but yeah. And then the configuration space is also just 2-dimensional.
Okay, so somebody.
Yeah, actually, the configuration space is 4-dimensional.
Uh-huh.
I think you have x, y, theta, and phi also, because like phi is important for the position of a point on the front axis or front axis wheels.
Mm-hmm.
So to encode that, you somehow also need that degree of freedom, right? So I think we have 4 degree of freedoms, and like translates down into the configuration space.
Mm-hmm. What about the workspace? Or there's even more complaints or ideas?
X and Y can be expressed by theta and rho, so it's actually just the same 2 degrees of freedom.
X and Y can be expressed by theta and rho. I think, the rho, that's, yeah, interesting, yeah. I mean, if rho is given, that's true. Mm-hmm. Any other opinions?
Yeah, regarding the workspace, I think it's still the R2.
Okay. Okay, another opinion, yes?
I think for the degrees of freedom we have 3, x, y, and rotating around z,
Uh-huh.
so that can rotate in the same place.
Okay, so we have many opinions. And I would say most of them were also correct, which is cool. So maybe for degrees of freedom, what's important, there's another related term which is kind of controllable degrees of freedom. And so what you said at the beginning was, I think, more related to that. Like you can only control 2 things for a car, but the degrees of freedom are still kind of 3 things. And that means it's kind of under-actuated, right? Like this car cannot freely move in the space, but it's kind of constrained by what you can do with the wheel. And the controllable degrees of freedom I didn't really introduce here. So degrees of freedom, I would say, is 3 here. I think whoever said it was 4 is actually also correct, and that just depends on how exactly you define how the car can be controlled, which I haven't really talked about here. But if you can only change, so if you can directly change this angle here as part of your control, then it does not need to be part of the configuration. But if you can, every single time you make a change in your steering wheel angle, somehow limited, maybe only by 10 degrees, then it would become part of your state and you would get a 4-dimensional configuration space. So that was basically also correct. Yes, and workspace I would also say here too. Okay. Yes. I mean, one thing, there's one comment I still find interesting about basically the polar coordinates. Because that would then decrease the degrees of freedom if we would encode it with theta and rho. I have to think about that. Yeah?
Why is phi not part of our normal configuration? I understand that we can describe the position with the theta angle, but it still describes the state of our robot in terms of the angle of the wheels.
Yes, so it would also be correct to add it. It depends on the controls. So some people would say phi is part of the controls, which we haven't discussed here. Or you say it's part of the state or configuration.
But even if it's not part of the controls, it still describes the state.
Yes, but then you try to have a double in there. So typically you don't, if it's directly a control signal, which means you can instantaneously change it, then you typically don't put it as part of the state.
Okay.
Yep. Okay, but maybe also important to note here is that for many of these questions, it's not necessarily like one fixed correct answer, right? But it's kind of important to get a feeling about it. because it defines to some extent the complexity of your planning problem, right? Like if maybe the difference between 2 or 3 dimensions is not that big, but if you have 2 or 20 dimensions, it's a much bigger difference. And we all agreed that it's basically somewhere between 3 or 4 dimensions, right? Depending on how exactly we phrase it. Okay, then a little bit more definition. So what we also will need is what is known as a configuration map. So the configuration map basically specifies, given some configuration Q, which points are occupied by the robot. And that typically depends on the shape of your robot. A very simple way of doing it would be for a circular robot. So assume you have a robot that is kind of just a filled circle, and that circle has is centered at this x naught and y naught and has radius r. Then the configuration map just describes all the points that lie inside the circle. And so this equation should look familiar. So it's basically really all the 2-dimensional points, x and y, such that this condition over here is fulfilled, and that condition with the equal sign would be just the kind of equation of the circle itself, and then it's smaller or equals to also include the points that are inside the circle. Okay, and then we talked about the workspace, not so much about the obstacles, and then we typically also separate the kind of space that are obstacles and the actual free workspace. And so if we have some sets of obstacles, so these would be just points, like in this case, for example, O1 could be all the points by this rectangle, or 2 all the points by this rectangle, and so on. So it would go on up to O4. Then the free space is just defined as the whole workspace, and then without the union of all the obstacles. Okay, and with that we can start with the first kind of important definition of motion planning. So here we are at the geometric motion planning problem. So ideally, as input, we want to have some sort of description of the environment, of the robot shape, of our initial configurational state and our goal configuration. And the output should be the sort of sequence that tells us how can we go from the start to the goal without collisions. And so that's nice, but we have to try to do it more formally, and so we get the thing that maybe looks a little bit scary at the beginning. So we start with the precondition. So given some initial configuration, which we call just Q start and Q goal, so they're both elements of our configuration space, and some definition of the free workspace and our configuration map. Some cost functions that tells us how good or bad our solution is. We try to find the sequence of configurations. And so basically we have some constraints. So the first constraint says, or it's the beginning of the sequence, so if this variable or this function is 0, then we need to be at start. At the end of the sequence, so Q of 1, we need to be again at the goal. And then for any element in the sequence, so for this progress variable that I call P, any of them or all of them between 0 and 1, it needs to be that if I take the configuration where the robot is, I apply this map which tells us which points are occupied at this like progress basically on our path. And then this definitely needs to be a subset of the free space, so it cannot be in collision with some of the things in our environment. And then there might be many, many solutions that fulfill these 3 constraints that I have down here. And I'm interested in the one solution that minimizes this cost function j. And the cost function j gets as argument the solution. Yeah, and then what do we minimize over? We minimize over the sequence Q. Okay, any question about this definition? Okay, so maybe some notes. So what I find most annoying by this definition is that it seems a little bit impractical, because we have this analytical function Q of P, which sounds like it's a smooth function, but like how would I define it formally is pretty difficult. So what people often do is instead having a sequence. So we just kind of look at different points on the path and say we get like these discrete points. The reason why we didn't put it in the original definition is that if you have a very narrow obstacle, you could miss that you hit an obstacle. So one example could be this curtain over here, right? Like if I plan a motion from this side to the other side of the curtain, and I have a sample point here and a sample point on the other side, and then I check that all the samples are collision free, then that will be true, but I will have to go through the curtain and I will hit the obstacle. That's why it's very difficult to kind of correctly define it just with discrete samples, unless these samples are really much closer than the smaller size of the obstacle, right? But in practice, that's still what we often do. Maybe what's also important is that we have this progress variable p between 0 and 1, and it's kind of easy to think about it as time, and it's also not necessarily wrong, but it's really more like a sequence. So that means if I'm at 0.1, that doesn't mean as it's as far from the beginning as 0.9 is away from the goal, right? It could be different. Like I could still move with like a non-uniform velocity profile along this path. So for geometric planning, we don't reason about time. We just reason about kind of a motion in general without assuming time. What we most of the time do is that we assume that the cost function is shortest path. Seems logical. And that would be also fairly easy to define. And then this kinematics constraint that just tells us collision freeness. Sometimes you don't use the configuration map, but instead you assume you're given this free configuration space, and then this condition just becomes that Q of P is an element of Q free. But defining Q free is actually much harder than defining this free workspace. Okay, so how does it look in practice? So if we would now take this example, put it to a solver, then what the solver would do is something like that, which is kind of collision free. It's maybe not exactly what we expected, thinking this is a car-like problem. Okay, so when we think about robots, we have this issue that for many robots, just thinking about the spatial dimension is not good enough. So if you have this forklift, for example, it carries this heavy load, which means it cannot brake instantaneously, similar to a truck. So you need to account for these very long braking periods. If you have these sort of drilling robots, kind of a similar thing, they can't really turn in place, right? They have these very large turning radii that you need to consider. And then finally, for the flying robots, there's also this problem with the downwash I talked about at the beginning, and that the flight dynamics are pretty far away from just moving some body in 3D space. And so robots, generally speaking, are subject to what's known as kinodynamic constraints, where kinematic constraints are kind of these geometric constraints that we already talked about. And dynamic constraints are some sort of temporal constraints that tell us how we can move with respect to time. And they can be both coupled in principle. So if you think about driving a car, then if you're on a highway and you move at a very high speed, you cannot really take a tight turn. But if you're in the city, you can you stop almost, and then you can do these 90-degree turns. So really, geometrically, what you can do is also define what happens on your temporal level. And so to model that in terms of motion planning, we need to somehow have a model on how the robot can even operate. And that is known as robot dynamics. And for robot dynamics, we need to first add some more definitions again. So what we typically have is this control or action space, which defines what can we do to our robot in order to make it move, for example. So if you have a car, then there's different models, but the most easy model is that you say, I can directly control the speed instantaneously, and I can directly control the steering angle instantaneously. So that's the most simple model we can come up with. And in that case, our control space would be two-dimensional, and our control actions would be just these two scalar values. One is the speed s, and one is this steering angle. Okay, and then we also need to define what will happen to the car if I apply these actions. And that is typically defined by the dynamics. And the dynamics are a function that take as input the current state and the action. And they basically output either the change of the state or the next state, depending on if you want to use it as a differential equation or more like a step function. And so if we again take the example of the car, then we have here the configuration space, for example, is now just x, y, and theta, so the yaw angle of the whole car. Our action space is just the speed and the angle of the steering wheel. And then the dynamics are basically given by these three equations. And in compact form, it would be this form where everything is a vector, right? Q dot would be the vector of x dot, y dot, and theta dot. So the output is a three-dimensional vector. And then the function also gets as input two variables. Q would be another three-dimensional vector, and U would be a two-dimensional vector. But if we write it component-wise, those are kind of the components of the function f. And that basically means x dot, which is the change in the x coordinate, is just the speed of the robot times the cosine of the current angle. The change of the y coordinate is the speed of the robot times the sine of the current angle. And then maybe the most difficult one would be more the change of the angle itself, which depends on how fast you move, how kind of long the distance is between the front wheels and the back wheels, and then finally what you do with respect to steering. Okay, and then we can now basically come up with a more or different definition for these sort of motion planning problems, and this is now known as kinodynamic motion planning. Our input still stays the same. This maybe is one difference, that we also need to describe how the robot itself can move. But the output now has these additional constraints that we need to make sure that we kind of follow these limitations that our robot has. And so if we write it down formally, it becomes again this really long thing that we have to maybe pause first. So I suggest we start with the constraints. So we still have this constraint that at the beginning we started our start configuration. And then at the end is now not 1, but this uppercase t, and the t is really now the time duration. We want to reach our goal, so no surprise here. And then we still have the third constraint, which basically tells us for all the intermediate configurations between 0 and t, we need to be in our free workspace. And then what's new here is that we have this fourth constraint that basically tells us that the change of q needs to follow our function f, which is the description of how our robot can move or our robot dynamics. And it needs to do that also for the whole period, except now not for the very last step, because there we don't really care. So we have that encoded, and then the question is, what do we optimize? So now we don't only want our sequence of configurations, but we also want a sequence of actions. So how do we get the robot to move from the start to the goal? And actually what's sometimes the most difficult is that we want to know the time horizon. So we don't want to say, oh, in 10 seconds I will be at the goal, but maybe I want to be at the goal as fast as possible, which means that time horizon, t, needs to be a decision variable as well, and an output of our algorithm. And since all three are decision variables, our cost function now also gets all three of them as input, and basically defines which of the kind of infinite many solutions is the best. And then again, we just pick the sequences that minimize this cost function. Okay, any questions about this definition? Okay, then also some notes about that. So like in the geometric case, it is more practical to actually use these sort of discrete sequences instead of this analytical function, q of t. The most common cost functions here would be either time or energy. And so I think there's some exercise about maybe time, but energy, one example is that you only consider the control actions u, so you assume every time you apply some action u that costs some energy, so you just take the square of that and you sum them all up, or more generically you take the integral over all of these actions that you take, and then you want to minimize that. And I like to call it kinodynamic motion planning, but in the literature, if you look at some of these reference books, there are also other terms. So a common one is non-holonomic planning, because you typically apply it to robots that are non-holonomic, that cannot move anywhere in the space. Or people also call it control space planning, because the output now is not just a sequence of configurations, but the output will also be the sequence of control actions. Okay, and then if we apply this to our little example problem, we get something that is maybe more what we would have expected in the first place, where we find a solution. And here we also can nicely see maybe the importance of optimality, because there's many different solutions, but most notably, most motion planners will first find a solution that goes kind of around, because there's more open space, it's easier to find. And then if you have a narrow passage in the middle, it's much more difficult to find this sort of solution. Yes, looks. So I did one here. I also don't know why it's all closed up. Yeah. Okay, any questions so far? Then maybe let's talk a bit more about some terms and other things. So the difference between geometric and kinodynamic motion planning also defines maybe the difference in some other terms. So often when we say path, we mean just a sequence of configurations, but we don't really care about the temporal component, which also means path planning typically refers to our goal of finding a path. When we say motion planning or trajectory, then we refer to as a sequence of configuration time pairs specifically. And that also means that if we do geometric planning, that means we do path planning. If we do kinodynamic planning, then that is really what I would call motion planning. Sometimes people in the literature mix those things up. We try to be kind of more specific here. Just be careful. And then, of course, the question now is like, okay, we have these kind of two definitions. They looked fairly different. One was much longer, had like more constraints and so on. So it seems maybe like natural to analyze what is exactly, mathematically speaking, the difference between geometric motion planning and kinodynamic motion planning. And that will be already part of the first exercise that you discuss also tomorrow. I think that's the only question on that exercise sheet that is like really difficult. The other ones are more applying these definitions to more examples. And just kind of as a hint, just really go by the definition, and the question kind of tries to guide you through it, but try to see if you can like convert one of the definitions in the other into the other and vice versa. Okay, and then another common term that you will find, maybe also if you've taken other robotics classes, is this term of collision avoidance. And it's very often mentioned when talking about motion planning. And even in motion planning lectures or books, there's sometimes chapters about this. And the way collision avoidance typically works is like one example is this potential field, which assigns these virtual forces. There's one force that pulls you towards the goal, and then there's typically a whole set of forces that repel you from any sort of obstacles. And then the algorithms in collision avoidance very often, for example, follow just the gradient of the resulting force. And the problem with these sort of settings is that there are singularities, so there are spaces where there's no resulting motion. So you can kind of see it here, where there's a singularity somewhere here, where the resulting force is exactly zero. So if you follow the gradient, you would be stuck there forever. And what that also means in practice is that these sort of collision avoidance methods, they are reactive. And reactive just means you don't reason about a time horizon, but you just take your current state as an input and you directly output what you should do, like the next time step, basically, without considering what might happen in 10 seconds. And so, to me, the difference is that planning is always reasoning over a time horizon. If I just do something reactively, then it's not planning. It's just controls, I would say. And so we won't discuss it in this lecture. So we only look at real planners that can deal with a time horizon, and most of the algorithms we look at even support dynamic time horizons where we do not know if we need to plan for 5 seconds, 10 seconds, or 10 days. Okay, to conclude, so today we basically motivated motion planning as part of the robotics pipeline, the traditional one as one module of decision making. We looked at many examples. Some of them were not surprising in the area of robotics, others in biology, or these computer games were maybe not expected. And we learned a lot of these new terminology that we will use from now on throughout the course. So specifically the configuration or configurations or states and the state space. The degrees of freedom, which describes the minimum dimensionality of our configuration space. The configuration map, which tells us, given a configuration, which volume does the robot occupy. The action space, if we have a robot that we can directly control. And based on these definitions, we define geometric planning and or path planning and kinodynamic planning or motion planning. And next week, Andreas will be talking about some foundations for manipulators, operating not only in 2D but in 3D, and also how can we actually efficiently do this collision checking where we try to figure out if we are really in the free workspace or not. Before I close, here's again a list of these suggested readings. So the first one is this tutorial on math, and then there are specific kind of subsections in the three different books I pointed out that just also talk about these definitions and terminology. And then if you don't know yet, there's this robotics interest group on ISIS, where I recommend to sign up just to get updates on what all the at least 4 big robotics labs do at TU Berlin in terms of teaching and research. Thank you.